Hi guys, welcome to the video on redox titrations. In this video we're going to look at what a redox titration is and how to do calculations involving redox titrations. So as you watch this video, if you think that maybe you need an extra resource or you want to watch a different video on redox titrations, there is this link that is on the class website. This is a Khan Academy video. I think it's 6 or 7 minutes long, where he actually walks through redox titrations as well and talks about really what happens in the titration itself, and then he just shows a quick calculation. So with redox titrations, we've done titrations before. We've done acid-base titrations to determine the concentration of an unknown acid or base. The only difference now is in a redox titration, we're using it to determine an unknown concentration of an oxidizing or reducing agent. So all we're doing is we're just finding a different unknown concentration now. The difference with redox and acid-base is that the reaction needs to have a 100% yield. So what that means is it needs to go to completion. You cannot have excess of either reactant. And then there also needs to be a color change to indicate when the reaction is complete. Typically we use potassium permanganate, KMnO4, which is actually purple. So when you add the KMnO4 from the burette into the flask below, once you complete the reaction, the flask below will actually turn purple as well. And there are other indicators that you can use, but typically once something undergoes oxidation or reduction, it will actually change color on its own, and that actually can serve as an indicator. So at the equivalence point, remember that the equivalence point is when moles, we remembered moles acid equal moles base. Well, at the equivalence point, the moles of titrant, which is what's in your burette, equals the moles of analyte, which is what's in your flask below. That's important as we go through stoichiometry. So we will use stoichiometry because it's hardly ever a 1-to-1 mole ratio. So what we're going to do is, if we're given grams of something, we're going to go to moles, use the mole ratio to find moles of our unknown, and we can also use volume. Now as we work through, you guys are going to be doing a lab on this as well. This link is also on the class website, or you can just type it in from the video. But this is a YouTube video where there's actually a teaching assistant at the college level, and he sets up a redox titration, and he talks about what happens during the titration. This also is about a 6-minute video. I would highly recommend that you watch this just to make sure that you're completely familiar with redox titrations, how they're similar, and how they're different from acid-base. So we're going to look through one example together, and then you'll have another video that will have more examples on redox titrations. So in this example, we're looking at potassium permanganate reacting with oxalic acid in acidic solution. So remember, it's important for acidic solution because that helps us balance our redox reaction. So here is the balanced redox reaction. Now keep in mind that if I just told you that KMnO4 reacts with oxalic acid, you need to be able to tell me what those oxidize or reduce into, and those are where those tables from your notes come into play. So in those tables it said that the permanganate ion, because why can we ignore potassium? It's a spectator ion. Everything with potassium is always soluble. So the permanganate ion always reduces to Mn2+, and then oxalic acid, this carbon is going to be changing oxidation numbers to get to CO2. So you could actually write the products and then balance it because you know it's an acidic solution. So if they gave us the problem that said 0.2585 grams of oxalic acid is dissolved in 100 milliliters, 0.5 molar H2SO4. Okay, so we had to acidify it. That's why this says an acidic solution. Upon titration and adding 22.35 milliliters, a faint purple color persists. What is the concentration of the KMnO4? Alright, so first thing, we always are going to do stoich. We know that we're finding concentration of KMnO4, and we know the volume. Right? We know the volume of the titrant. Okay? So we need to figure out concentration. So if we look at this balanced equation, here's what we know. We know that we have 0.2585 grams of oxalic acid, and we know that we use 22.35 milliliters of permanganate. We're trying to find the concentration. So whenever you're finding the concentration, you need moles and you need liters. So we're just going to go through the stoichiometry. Start with grams of what you know. We know the grams of oxalic acid go to moles, right? When in doubt, go to moles. So we're going to go grams of oxalic to moles of oxalic, then use the mole ratio. We know the mole ratio from the balanced equation. That's why it's so important to balance the redox. So for every 5 moles of oxalic acid, we need 2 moles of permanganate ion. That gets us this point 0.011,489 moles of permanganate. Notice how I took it out, quite a few significant figures. Then you divide by the volume of permanganate, right? Moles over liters. So if we take a look at this again, right? We had all this given information. We find that the concentration of permanganate, which in turn is the concentration of potassium permanganate, because it's 1:1, is 0.0514 molar. So that is the concentration of the permanganate. So notice the only difference between this and what we've done before is it's just balancing the redox reaction, but you're still using stoichiometry the exact same, just like you did in the strong acid, strong base titration.